Good morning, good morning, good morning. Episode 455 of Words Matter. And I have to say that episode with Mike Hildebrand was absolutely phenomenal.
Unbelievable. If you missed it, it was just last week, July 18th. Go check it out on the YouTube channel. Lots of fun. A lot of things going on in there.
And stay tuned. Stay tuned for the next one. After we get a good schedule, we'll be releasing the next AARP one.
I know it's going to be, I know who it is. It's going to be Mr. Bob Ingram.
Oh, Chief Ingram. I'm very excited.
Yes. I don't think we ever settled on a date yet, but I think it might be getting very firm soon. So, yeah.
We're getting things set to send our team out to the Chicago area for the Battery Destroyers 3. And the moment we have all of those videos formatted and post-production, we will do a show all about what we got.
And continuing challenge September 3rd through 6th, where you can see Mr. Mike Monaco presenting a medley of things. So if you're in the California area or the West Coast, you're going to probably want to check that out because there's some cool things we're throwing out at that one. And I believe I'll be at the Virginia Hazmat Conference on September 10th to the 13th. So
I think I'll do a throwback to the old Hazmat Jeopardy that we used to do and call it Hazmat Potpourri.
Ooh.
I
like that. All right. So we are continuing on our pilgrimage to define words, abolish conflation, because words matter.
Yeah, it's
picking the right word.
It certainly does. So some of the back and forths that we're going to be going through today, the first set is going to be ionization versus dissociation. So what do we have, Bob, for ionization?
Okay. When I say I am ionizing something, ionization is the process by which an atom or a molecule gains or loses electrons to form an ion. So in the simplest wording, an ion is a molecule that is either missing or has one plus electron.
So when we look at the periodic table and we say, lithium has 3 protons, it therefore should have 3 electrons in order to be balanced. Anything above that, right, which would be the additional of an electron, or below that, which would be the removal of an electron, is going to give us a difference in charge, and that charge is a new ion, correct?
Exactly. If it's not in its natural state, electron-wise, it is called an ion.
All right. So if I were to ionize a sodium atom, right, I'm going to go from sodium or sodium plus, right, with the ion. I'm going to add an electron, and I'm going to go ahead and get what? Just regular sodium. So I'm going from the ion state to the non-ionized state, correct?
Right, because we've satisfied that deficiency. So this formation of ions can result in the creation of positively charged or cations, or on the other side of that, we can have a negatively charged ion, which is called an anion.
So we should be, as technicians, kind of familiar with the concept of ionization because one of the major meters that we use depends on this. And we often and very easily can do this with gases when they're exposed to a high energy source like heat or light. For the purposes that we do it all the time, UV light in our PID, photoionization detector, is ionizing gas as it goes past the light bulb.
Right. And that goes into a very important part, is that this requires energy to make it happen.
Yep. High energy, which is why UV light is used, because UV has a really good ability to knock an electron off substances. Happens to be why we get sunburnt for those of us that lack melanin in our bodies.
Right. So this whole operation of ionization. What? Huh? What the hell is going on? It's almost like I'm on a loop. Ionization. Jeez, that was impossible.
I think you got your alphabet ionized. You're missing a few letters.
Hell? This requires energy input to overcome the attraction between the electrons and the nucleus. You got to remember the nucleus is positively charged. Forget the neutrons, it's positively charged, so it wants to repel everything. But the electrons are negatively charged and it wants to attract to everything, right? So it is this push-pull thing that sets that distance. And when they both agree, okay, you stay there and I'll stay here, that's how they kind of get together. And so you need energy to overcome that. And that energy that is needed to overcome that agreement is called the ionization energy, the IP.
You know, sometimes the question is asked, well, then why doesn't the electron just continue into the nucleus if it's being pulled that way? And I tell them to talk to Schrodinger. He'll be able to explain it to you.
Yeah, it's the protons that keep it from crashing into the planet.
Right.
Right. It's that rejection that keeps them away. And then the electron's like, no, come back. And say, no, please stay away.
It's a very toxic relationship. All right, let's chat about dissociation. All right, because often ionization and dissociation are used in conjunction with each other, but there is some slight differences. So dissociation is the process in which a molecule splits into smaller particles, such as atoms, ions, or radicals. It's a larger. Dissociation is almost a larger box that ionization is in.
Right. So in ionization, we are taking an electron away or removing it either permanently or temporarily, right? But in dissociation, we're breaking the chemical bonds within a molecule. Right. So I'm actually changing things.
Right. And this actually results in the formation of an ion or a neutral molecule from a larger molecule. So almost like when people chip away at rocks and a little chunk of a rock will come off, right? That's like matter coming off, where the ionization, you're pulling an electron. Electron really, it can't really be described as matter, even though it sort of is. You're talking about a larger chunk, a piece of matter coming off, and that would be your dissociation.
Right. So like if we take table salt and put it into water, right, it will dissociate in water to sodium and chlorine. Right.
But at the same time, it's ionizing the sodium and the chlorine. So the electrical charge is associated with the ionization. The dissociation is associated with the process of the two substances coming apart.
Yes.
Okay.
Yes.
All right. It often occurs when ionic compounds dissolve in water or any other solvent. So this happens. It happens quite frequently.
Right. And so here are some of the key differences between it. Let's talk about the process. The ionization, go with it.
All right. It involves the gain or loss of an electron. It forms the actual ion.
Right.
Right. So we have the ion here. The dissociation involves the breaking of the bonds in the molecule to form smaller particles, and an ion or a neutral molecule can be formed. So these things are happening at the same time, which is where the confusion between the two arises.
Right. Now, another key difference is the energy. So ionization, it requires energy to remove or add the electrons, where in dissociation, it usually occurs when a compound dissolves in a solvent and may release or absorb energy depending on the substance. So again, ionization, PID. Dissociation, me stirring some salt into water.
Yep. So if we're going to ionize, let's take the form of like hydrogen gas. Let's ionize hydrogen gas. We would end up with H plus and a negatively charged electron. If I'm going to look at dissociation, let's take a look at hydrochloric acid, HCl. I put it in water. That HCl is going to break apart into hydrogen and chlorine with their respective positives and negatives.
Love it. Now, let's go into another set of words that you probably didn't even know you didn't care about.
But again, you do, and it is a very small difference. And I promise you, the only people who are going to notice the difference is the chemist that you're talking to when you call up. If you were to call up a manufacturer and be like, hey, I need help, where's your lead chemist? And, you start going through and you're like, okay, yeah, it has a molarity of 10? And they're like, no, that's a molality. And you're like, yeah, that's what I said, molarity. And they're like, no, molality. And you're going to just listen to this and we'll make it clear as mud.
Right. So we're going to talk about molarity and molality. One's an R, one's an L. So molarity, okay, which is the big M, right? So if you look at this as the unit measurement or the discussion of this on paper, it would have a capital M.
Right. Or if you're looking at the bottle of like a hydrochloric acid.
Yeah, right, exactly. So the definition of molarity is that molarity is a measurement of the concentration of a solute in a solution. And it's expressed in the number of moles of solute per liter of solution.
Okay. So I feel like we need to define what a mole is for people. Because I think most of the people are going to go, what the hell's a mole? Right? Because the unit of measure for this is moles per liter. But if I tell you, hey, you're going 4 parsecs per minute, and you don't know what a parsec is, and yes, I know that was part of the joke, then you don't know what's going on. And a mole is a way that we can count molecules, right?
Actual atoms.
Atoms.
If memory serves, and I'm doing this off the top of my head, I think it's 6.023 times 10 to the minus 23rd atoms per mole.
Plus 23.
Plus 23. I'm sorry.
Plus 23.
Not negative 23.
Yeah.
So here's a great analogy of how big that is. I heard this when I was a professor said this, and I blew my mind. Is that if from the second you were born until the second you turn 100 years old, somebody gave you $10,000 every second for your entire life of 100 years, you wouldn't be 0.01% into a mole.
Wow.
That's how big we're talking. We're talking a stunning amount of atoms in this thing. So when I say that it's the measure of the concentration of the solute to the solvent, that's what I'm talking about.
Yeah, and it's a legit measurement. For those that are like, I don't understand why we would measure like this. It's because we talked last episode about compounds and mixtures and how a compound maintains a ratio. And we used water as the example where there's hydrogen and there's oxygen. Well, let's pretend that I'm a chemist and I want to go ahead and I want to make water. Well, I would go down to my inventory and I know that I have to grab 2 hydrogen molecules for every 1 oxygen molecules. But I can't just grab them, right? I can't just reach in and grab 2 hydrogens. I have to weigh them out. That's the only way I can measure anything. Well, if I were to weigh 1 gram of hydrogen and 1 gram of oxygen, hydrogen weighs so much less than oxygen that I'm going to get very little oxygen and I'm going to get a whole ton of hydrogen. So the mole is the way to figure out how to get the exact same number based upon weight every single time.
Right. So and molarity is going to depend on the volume of the solution.
Right. So we have a certain number of molecules per total volume.
Right.
All right. So if I were to dissolve 1 mole of sodium chloride, which again, a mole is just a number of molecules. Okay. If I were to take this number of molecules and number of sodium chloride and dissolve it in enough water to create 1 liter of solution, that is 1 mole, 1 molarity, 1 big capital M.
Right. And so this is, and there you have to consider also temperature sensitivity, such as molarity can change with temperature because the volume of a solution actually expands or contracts with temperature changes.
Okay. Now to molality. Lity, small m. The definition of this, a molality is the measure of the concentration of a solute in a solution expressed as the number of moles of solute per kilogram of solvent.
Ah, there it is. That's the game right there. One was by volume and one is by weight.
Yes. So big difference, right? If it's by weight, then we know like it's not going to be temperature dependent or anything like that. So the mole depends on the mass of the solvent, not the volume of the solution.
Right. So in this one, we're not doing moles per liter. We're doing moles per kilogram.
Right. So molality is not affected by temperature because mass doesn't change depending on my temperature like volume does.
Right. So let's just bang out a couple of the key differences between these two. First, and probably the biggest part, is the measurement. In molarity, we're talking about the based upon the volume of the solution, whereas in molality, we're talking about the mass of the solvent.
If we look at the units, right, because we're doing volume versus weight, a molarity would be moles per liter, and molality would be moles per kilogram. And just remember, don't get confused with the whole mole thing. It's just a certain number of molecules.
Right. And so our temperature sensitivity, does temperature affect it? Well, in molarity, it changes in temperature because the volume changes, but in molality, weight doesn't change with temperature, so it's independent of it.
Yeah, so if I were to dissolve 2 moles of sugar in 1 liter of water, or to create 1 liter of water, I would have a 2 molarity solution. If I did the 2 moles of sugar and I dissolved it in 1 kilogram of water, I would have a 2 molality solution.
Good stuff.